Well, first, thanks to the organizer for giving me the possibility to talk about the work I've been doing with people at INRIA in Software Heritage and Paris Telecom for this new Rust analytics for software heritage. I'll try to explain what we did. There's Stefano Zacchiroli, you already heard him speaking, and Tommaso is a student of our university that was actually hired to work on the project, and we worked very intensely in the last 10 months programming like crazy. It was very interesting, and I'm going to explain you why we did this. So first of all, who am I? I'm the head of the Laboratory for Web Algorithmics, which is a laboratory that was established in the late 90s. It's been a long time at the Università di Studi di Milano to treat specific algorithmic problems related to the web. And then we also expanded into the study of social networks as they became more prominent. Beside publishing papers, we have a lot of open source projects of various kinds. For example, we have a Java library for high-performance container that is used by more than almost 800 open source Java projects in the Maven Central. So we publish stuff that's used by the community, not only academic results. But what we try to do is to try to have strong theoretical results that have an impact, an actual impact on the industry. You can use them somehow. And you also write the code that make you able to use them. We also did a lot of data harvesting, in particular in the late 90s and the first 10 years of the 2000s, creating a very large database of web snapshot and social network snapshot that have been used in hundreds of publications because they are there. You just download them and you can use them. And it's a lot of work to gather web data. Now there are organizations like Common Crawl that do that. But at the end of the 90s, no, there was basically nobody. So what is graph analytics at scale? So today we found large graphs all over the place. If you don't know what is a graph, it's a very abstract representation of entities and correlation between entities, in which entities are the circles, and there is an arrow from entity to another entity, like people and followers on Twitters, okay? Or web pages and link between web pages. They're all subsumed by the abstraction of a graph. Yeah, web snapshots, social network, there are biological graphs like protein becoming other proteins through chain reactions, metabolic path. Many types of data can be represented as graphs. And today, you know, we have a lot of graphs from the internet in general. So they can be a graph of the web, friendship graph, follower graphs, and so on. And these very large graphs require new approaches, basically because the standard representation of this graph are too large to fit in memory. You need several terabytes and distribute. And so either you have money for a machine with, I mean, there are not a supercomputer, but if I think a supercomputer is not that easy because then you have to manage in a central location in core memory all this data. Most of very large supercomputers have separated memory, and graphs are very intertwined data. So they are not easy to separate in block to analyze separately. At Facebook, they have a whole bunch of algorithms just to do that, because it's very, you know, when your Facebook page goes up, you have to show your friends. Your friends might be in different servers. So it's, even that is complicated. Another possibility is to distribute everything. But what happens is that you spend so much time moving around data that actually distributing data might not really help you. There is a very famous paper by Frank McSherry called The Cost of Parallelization, in which he claims that and measures that for many problems, if you use a distributed approach, no matter how much hardware you use, you cannot be as fast with a laptop with a single thread for graphs that will fit a laptop with a single thread. So there is a very large cost in distributing that is not obvious. Replicating the hardware would not just do the job for you. So what can we do? And what we do is we have frameworks for graph compression. So we represent graphs in much less data, like 20 times less space, so you can actually analyze them not on a laptop, but maybe on sizable hardware. And the main product, let's call it like that, is the Web Graph Framework, which was developed about 20 years ago. It's one of the most long-lived projects of this kind. There are hundreds of publication and major conferences who use the data from the gathered and compressed with WebGraph or directly WebGraph. And like in 2011, maybe you read at the time the news that Facebook had 4 degrees of separation. There were also news on the New York Times about that. The 474 is because they read the paper incorrectly. Okay, it should be 3.74, but it was too late. It's also on paper. I'm so sorry. Now that's because sociologists measure degree of separation, measure distances, and there is an off by one, and there was a mistake in communicating the results. So, but then that was done at Facebook in collaboration with us using WebGraph. And I'm sorry for the little piece of the slide that's missing. That's my fault. But essentially, at that time, Facebook would have 700 million nodes, and we compressed it in around 200 gigabytes of space. So it was very easy to analyze on a reasonable hardware that costed like $5,000 almost 15 years ago. Okay, so what is the, you already heard about this, but let me give you a little bit more data. So the software heritage historiograph is one of the larger graphs of human activity available. I mean, probably we could gather a larger snapshot of the web, but presently there are no such large snapshots of the web. It is really big. I mean, it has a 500 billion arcs. And essentially, you cannot put this easily in a database or in an object-oriented representation in memory because you have a 500 billion object and that is not going to work. It's constantly increasing in size, and we are able to represent it by WebGraph using just 176 gigabytes instead of 4 terabytes of space. So you can actually have a visit. Presently, I will tell you later, but the Rassem implementation makes possible to scan, visit, as we say technically, the whole graph in less than 3 hours, which is an incredible feature because if you would distribute it use it in a distributed fashion on many servers, it would probably take days just to move around all the amount of data continuously between the servers. And what is presently done in Software Heritage is there is a WebGraph-based pipeline written in Java that was born out of collaboration with us, with the University of Milan, in REI Software Heritage. I would say 3 years ago, we started this, something like, I have very bad memory. I think it was something like 3 years ago. We actually met because of a European project in which Roberto and Stefano were the advisors, and they told me, we have this problem. And I said, maybe we can help. And it turned out we could actually help. So having the graph there explicit as a standard data structure makes it possible to do many things like provenance analysis, plagiarism detection, etc., at an unprecedented scale because you don't go through the hassles of like a distributed database. I can tell you this episode, when we did the Facebook thing, I presented the paper in 2011 at www, and Lars Bäckström, who's now the head of search at Facebook or of the feed or one of the senior managers at Facebook, had tried to do a visit of a Facebook graph and just received a call from the engineers saying, you're tearing down the database, you cannot do that on a distributed database. So he had tried, but he wasn't able. Then we compressed it with WebGraph, and we were actually able to measure the degrees of separation on the graph. Nonetheless, in the last couple of years, Java is getting in the way for a number of technical reasons that maybe are a little bit too technical, but let me explain you why we want to move to Rust to do this. This was an idea proposed actually by Stefano because I have been interested in Rust as a language for a long time, but it's been maturing over time. And the last year, things start to move into place and the language started to become much more usable. It's a new high-performance, safe language. High-performance means like C++. Okay, so you can really get to the memory cycle. It's memory safe as Java, but it has a zero-cost abstraction. So there are abstractions that are very powerful, but you don't pay for that because the compiler makes essentially everything cancel away once you compile the code. Arrays can be as large as memory allows. If you've written in Java, you know you're limited to 2 billion elements. If you have a 500 billion edges graph, 2 billion elements start to become a great problem. There is a very nice access to the operating system facilities and a modern function-inspired idiomatic programming. There is a very nice talk about invariance of type, invariance of lifetimes, technical topic of Rust, in which the guy, even the talk starts saying, Rust is the only language in which you have to think in category theory, but then you have to think about the cache accesses. Because you constantly have these two very abstract mathematical level in designing the code, and then you really bang on the hardware and do hardware performances. And it's quite unique in this. So it's fun to write. It makes it possible to us. It makes it possible for us to express very nicely the analysis we want to do on the graph, but at the same time, it's extremely fast and effective. It's also the first language last year to be integrated in the Linux kernel. It's the only language except C you can use in the Linux kernel. And it's being rapidly adopted by the industry. Like at Facebook now, if you write a binary, they suggest you to use Rust, not Python, not C++, and so on. So this is why Rust. So what we get? So there was this collaboration I told you ongoing. There is a student involved that was paid to do some work. We committed some 100,000 lines of code about in 8 months. There were 2 people writing actively, and Stefan was supervising and helping us with the design. Presently now we have 50,000 because we changed our minds a lot of times for the design. We tried a lot of designs before getting to what we are now. And so we have now a new graph analytics pipeline, which almost completely replaced the one developed in the last 3 years in Java. It's completely open to new compression models and 3 times faster. I mean, literally 3 times faster. Presently, if you visit the whole software heritage graph in Java, it will take 9-10 hours. In Rust, it takes less than 3 hours. So if you know this kind of stuff, getting a 3 times, 300% increase the speed is really, really nice. Because it took a year to do that, because we had to fill a series of gaps in the Rust ecosystem of software that were filled previously by our Java libraries, which we developed over 25 years. So we had to port a few things, but we released the several open projects to the community, and some are having quite a success. I mean, they've been downloaded thousands of times, so we're happy also about that. And what happens so that presently, I think that the pipeline, the analytics pipeline is ready for the future growth of software heritage, because we expect this graph to grow continuously. And of course, at some point, you will need larger hardware, better algorithm, and so on. But this first step is fundamental to move into like the 21st century, because we're moving from a language that was having major performance problems to a language that makes it possible to really get the best possible performance from the hardware that is available. And I think this will go in production pretty soon. We're still, polishing putting last polish on the libraries, but it's almost done. And I hope this will be, the start of a long, fruitful collaboration with Software Heritage.
Okay, so thanks a lot, Sebastiano. This was a brilliant presentation. And if I may add a comment here, you have heard the power of the community, power of collaboration, power of open source. You see this at play. Okay, we could tap in the mind of brilliant people like Sebastiano, thanks to Stefano, to get something that would have been unthinkable without this power of collaboration.